Okay, so this is our last lecture. So today I'm going to finish the part 3, which is also the last part of this chapter, chapter 6, which is an application of infinite series. Okay, so we are going to use infinite series to solve ODE. Okay, so but before going to this, I would like to give you one more example, okay, related to complex number that I talked about last time. So last time you learned the Euler formula, right? So at least the basic usage of this Euler formula, right? So is that this e to the I theta equals cosine theta plus I sine theta, right? And I kind of told you, well, although it was not a rigorous proof, but told you using this Taylor series, right? So to see why this exponential I theta is equals to this cosine theta plus I sine theta. Okay. So so what I want to do is just to talk about one example. Okay, so where we can take advantage of this formula here. Okay, so I think there's a problem that you have done before, right? So again, this example is an ODE example. Okay, so this in fact, if you are taking 2510, right? So I think one of the problems that you have done maybe 2 weeks ago or 3 weeks ago is to solve this ODE. Okay, and you know that the physical meaning of this ODE is actually a driven harmonic oscillator, right? So this is the natural frequency, right? So this is the damping, and this is the driving force, okay? So, and well, of course, you know how to solve it already, right? So you have this complementary solution, and then you try the particular solution, which is also the sine or cosine, right? So everything is good, right? So here, as I said, I'm just going to make use of this formula, okay? So to actually make things easier to solve. Okay. So what I'm going to do is that if you have this a cosine omega t, right? So which is actually the real part of this e I omega t, right? So the right hand side can be this cosine omega t can be written like this, right? So then what I'm going to do is to kind of actually rewrite this equation, right? So instead of using cosine omega t, I'm going to just use this ei omega t. Okay. But of course, right? So this is not really the same as what I just had, right? Because this ei omega t really has the imaginary part also, right? So really, the right hand side is just the real part of this, right? So, but what I'm going to do is actually to solve, right? So this slightly different problem, right? Just leave it as it is, and then at the end, I'm going to take the real part of the entire thing, right? Right. So the idea is that I allow this complex function to be a term. Okay, just solve it. Okay, so don't care about whether you have this real number or complex number. So complex number can exist, okay, in every step when you solve this problem. Okay, after you are all done with this problem, you just take the real part of what you got. Okay. So why is it easier? So first of all, right? So I'm not going to worry about the complementary solution anymore. But basically, I want to just focus on talking about finding the particular solution. Okay. So before, right, if you have this a cosine omega t on the right hand side, then the particular solution that you are trying to try also is also some sine omega t plus something cosine omega t. Right? And that if you substitute this sine or cosine over here, right? So you have to take the derivative of sine or cosine, and then every time you take one derivative from cosine, you get sine, and then from sine you get back to cosine. So you are alternating between sine and cosine and make things a little bit inconvenient. But now, with this form, what I'm going to do is simply let this particular solution simply in this form, okay? And again, we keep in mind that at the end of the day, after we actually find out the particular solution, we'll just take the real part, right? So here, right, so the C is some unknown number, right? So we are going to figure out, right? So we are just going to substitute this trial form of this particular solution back to the left-hand side to this equation and hope that this has to be equals to the right-hand side, right? So if you actually substitute that into the left-hand side of the equation, right? So what you have now, taking derivative is really convenient, right? Because whenever you take this derivative for this exponential function, you just pull out this factor of I omega, right? So if I go ahead and you realize that, of course, you always have this common factor C, and you always have this common factor EI omega t. Okay, so and then if you take the second order derivative, basically what you have is I omega and times I omega. And then the second term is 2 beta times I omega. Right? But whenever you take one derivative, you just have this extra factor of I omega. And then lastly, you have this omega naught squared. Okay. So this is what you have for the left-hand side. Right? So then, of course, the right-hand side is just simply this, right? So A EI omega t. Right? So now you are going to equate left-hand side and right-hand side. Right? So that means what you have is C times this whole thing here equals A. Right? And that means, right, so the C has to be this A divided by this whole term here. So, but now you notice that even all these constant terms here will involve both real and complex number, right? So, but anyway, so that's not an issue, right? So it's just that we are not at the final step yet, right? So let me just write the answer in the new page. So this particular solution is given by, right? So A divided by all these terms here. Okay. So now, right, so what do you need to do? Right, so you simply need to take the real part of this particular solution and you are done, right? So but now how do I take the real part of this solution, right? So you need a little bit work, right? So because here this one itself is a complex number and this one also is a complex number, right? So what I'm going to do is to convert the prefactor, convert this prefactor also in an exponential form, right? Because last time I said that, right? So any complex number can always be written as an exponential form like this. Let me just call this b times e to the I phi. Okay. So if I can do that, right? So then this whole thing, this whole particular solution is written as what? It's b e I phi times ei omega t, and then which is equals to b times ei omega t plus phi. So, and this is very nice, very neat, right? So because what you have now is just b is itself is a real number, right? So all the complex number is just contained in this exponential term, right? So if you just take the real part of it, right? So if you take the real part of it, it will just be b cosine omega t plus phi, then you're done. This is your particular solution, right? So, and in fact, if you go back to your homework of 2510, right, so you have also done it, right? So you eventually you find that your particular solution looks like this, right? And then you might still remember that the phi that you found is rather complicated, right? So now, right, so with that in mind, right, so I just all I'm trying to do now is to try to convert this prefactor into the exponential form, right? So the way that we do it is that this one, right? So I just write it again over here. So this one is real part plus imaginary part, right? So this is A plus BI, right? So then I'm just going to multiply by multiply both the numerator and the denominator by the complex conjugate of this, right? So then what you have would be on the numerator and then in the denominator, what you have is okay. A is over here. So from this step to this step, okay. So as I said, I'm just multiplying both the numerator and the denominator by this one. Okay. So the denominator becomes this. Okay. So now you can clearly see the real and the imaginary part in this expression, right? So of course, this would be the real part of this whole complex number, right? And then, of course, this is the imaginary part of your complex number, okay? So now, how do I find the B and this phi, right? So B this B would be equals to the square root of the real part square plus the imaginary part square, right? So, and what about phi, right? So the phi is actually the arctangent of the ratio between the imaginary part and the real part. So with that, right? So if you actually try to do it, right? So you'll be able to find that this E would be equals to 1 divided by square root of okay. And then the phi, you'll find that this is okay. So, and this would be not surprisingly is actually the exact same result that you got, right? So if you just basically use sine cosine as the particular solution and then play with all the numbers. Okay. So in fact, okay, so that is actually a slightly faster way to find this B. Okay, so is that basically you just need to multiply this thing, right? So by its own complex conjugate, right? So then that's also, and then take a square root, then also can give you the B. Okay, so so that's it. Just an example that I wanted to talk about last time. Okay. So now we actually come to the last part of this chapter, also the last part of the course, right? So as I said, right, so I'm going to use this infinite series to solve ODEs. Okay. So in particular, by second order ODE. So in the chapter of ODEs, right? So we have solved this second order linear ODE, right? So, but however, most of the time, we just have these two coefficient functions to be constant, right? So, and in that case, you just need to use find the characteristic equation, and then you know that your solution is either sine, cosine, or exponential function. Right? So, and we also have considered some cases where this P and Q are not constant, right? So, and we did have some tricks, right? So, for example, using some substitution. Right? So here, right? So we have another strategy to solve this kind of second order ODE, right? So where P and Q are not just constant. Okay. So, and the idea is to use power series. Okay. So what it means is really is that, okay, so I don't know the solutions. However, I hope that the solutions, right, so can take this form, right, a power series. And it's not unreasonable, of course, right? So because, as I said in the last part, I told you that as long as the function is analytic, right? So it can always be expressed as a power series. Okay, so that's why first, right? So I just assume that this solution, right, is this function is expressed as a power series. Okay. Then in that case, right, so then your job is to find out an, right? So then if you figure out an, then you know this function, right? So that is solving this ODE, right? So becomes a problem of finding an. Okay. So here is a very simple example where you know how to solve already, because here is still just a constant in front. Okay, but I'm going to use this well-known example just to illustrate the idea first. Okay, so well, first of all, you know that the solution is sine and cosine, right? So the methods, right? So the general procedure of the methods, right? So as I told you already, is that I let the solution, okay, so to be like a power series like this. Okay, and then well, of course, this is we expect this is a convergent power series, right? So that's why we can differentiate it by doing this term by term differentiation. Okay, so then that's why this y prime is written like this. Okay, so you can actually see that so it's very simple, right? The differentiation, because this x to the n, this becomes n times x to the n minus 1, right? So just a one slight details here is that you can see that this one go from n equals 0, and then this one just go from n equals 1. Right? It's just simply because for the 0 term, it's just a constant, right? So after you do differentiation, this one goes away, right? So that's why this one, the summation go from n equals 1. Okay. Well, of course, the upper limit, you never worry about it because it's infinitely many terms, so you always just go to infinity. And now, if you go ahead and take the derivative one more time, right? So you get the power series expression for y double prime. Okay, so then this is now is n equals 1, and then because you take the derivative again, the first term is again killed. So then that means it's the second term over here is killed. So that means that you go from n equals 2. Okay. So, but in fact, in this case, you can see that even you write it in a way that you go from n equals 0, it doesn't really affect anything, because if you just put n equals 0, right, so this n is 0 anyway. Right. So similarly, even here, if you write n from 0 go to infinity, you are not wrong, because if you put n equals 0 or n equals 1, right, so this factor gives you 0. Okay, so now I have this y double prime expressed as the power series, and then also the y expressed as the power series, then I'm going to substitute these two power series back to the left-hand side of the equation, of the differential equation. So then this is what you get. Okay, so first line. Okay. So if you just look at the first line, it doesn't seem to be so helpful, right? So you still don't know what ANs are. Okay, but then here comes to the key step. Okay, so which is known as the shift of index. Okay, so just focus on the red box. Okay, so of the first line and the second line. Okay, so what I do here is that you can see that I go from n equals 2 to infinity. Here I go from n equals 0 to infinity, but then the terms looks different. So let me write another expression on the side so that you understand what I really did to get from the first line to the second line. So what we are really considering is something like this. So let's say this n goes from n naught, right? So in this case, n naught is 2, but it can be any integer, right? So and I have some expression depends on n. Okay, so this is what I have in the first line, right? Essentially. So then the next step is that whenever I see n, okay, so I just replace it by n plus 2. So what it means is that I'm going to do this. So I see this n, then I just put this n plus 2 equals n naught to infinity. And then this f, I see n here, then I just replace it with n plus 2. Okay. So just make sure that you understand this left-hand side is exactly equal to the right-hand side. Right. So because basically I'm just using another index, right? So now from the right-hand side, I can further write it like this, right? So n plus 2 equals n naught. That means n equals n naught minus 2, like this. Okay. So just make sure that you understand these 3 lines. So and the final result is that, right? So from here, right? So you can go to this last expression here. Okay. And that what we did from this line to this line. Right? So as I said, right? So it's easy to remember. Okay. So is that whenever you see n over here, you just replace it by n plus 2. Okay. So why do we want to do that? Okay, it's because now in the first term here, it comes with this x to the n minus 2. Okay. And in the next term here, it just comes with this x to the n. So if I do this shift of index and such that I make the first term also comes with this x to the n, then basically I can write these two summation together, just like this. Okay. So and now this x to the n is just treated as a common factor over in this behind here. Okay. And then now I have this whole thing in the bracket. Okay, so you can see what do you have here? You have some n terms, you have the a n plus 2, and then you have this alpha, which is just a parameter in your ODE, and a n. Okay. So now, right, so this whole summation has to be equal to 0, right? And it has to be always true, no matter what kind of x that you pick, right? So and therefore, right, so it is required us to force this term in front itself to be 0, okay, for all n. And here I write it over here. Okay, so that is this whole coefficient by itself has to be 0, okay, for all n. So what it means, right? So it's a relation between a of n and a of n plus 2, right? So that means if you know a0, you will know a2. And then because you know a2, you use this relation again, you will know a4, a6, and so on. And this is all just for even, right? So now if you know a1, then you will know a3. If you know a3, you will know a5, and so on. So then you figure out also all the odd coefficients. Okay. So this recurrence relation is the key. Okay. So I just need to give you a0 or a0 and a1, then you figure out all the other coefficients. Okay. And this is actually how it works, right? So as I said, right, so if you know, so here, okay, so I can, let me further just write it one more time, is that now you see that this an plus 2 is equals to this minus alpha square divided by n plus 2 and n plus 1 an, right? So then put n equals 0, then the right hand side is a0 over here, alpha square, and then 0 plus 2, 0 plus 1, so 2 times 1. And then on the left hand side, you have a2. Right. So this is how you relate this a2 with a0. And then, so that's what I write here. And then from a2, right, so you can also relate a4 with a2. Right. So you relate a4 with a2, and then use the relation between a2 and a0 to finally relate a4 and a0. So similarly, here you relate a4 with a6 and a6 to a2, and then finally a2 to a0. Okay. So in fact, right, so for all the odd even coefficient, you can find this general formula over here. Okay. So similarly, right, same logic, same procedure for odd numbers, right? So you find that this a of n is given by this expression over here. So you can see that, as I said, right? So for any even coefficient is expressed in terms of a0. Okay. For any odd coefficient expressed in terms of a1. Okay. So that means we are done, right? So of course we don't know a0 and a1. Okay, so but these two are just two constants, right? So it can be taken out as a prefactor of your entire series. So that's why here I have put this a0 as the prefactor of the first series plus the second series using a1 as the other prefactor. Okay. And now, so that means that I think it looks familiar to you now, right? So you know that for second order ODE, it must be the solution for the second order linear ODE, the solution must be a linear combination, right? So for two solution, right? So then this is exactly the form, right? It's some constant times the first solution plus the other constant times the second solution. Right? So and I write it in a more tidy form over here. Okay. So and in fact, you'll notice that this series is exactly the Taylor series for cosine alpha x, and the second series is exactly the Taylor series of sine alpha x, and this is the solution. Right? This is what you expect, as I said, right? So because you know how to go back to look at this equation, you know how to solve it already, right? So this sine and cosine. Okay. So, and this two coefficients over here are just determined by this initial condition. So you can see how this series method works. Although, right, so this example does not really show you the usefulness of it, because as I said, right, so this example is too simple that you know the answer already. So here, right, so let's do an example, right, so that you probably don't know how to solve at first sight, right? So is that it's a non-constant function over here. Okay. So, but the same idea, okay? So is that you again, right? So assume that the solution take this form over here, okay? And then you are going to differentiate it term by term, right? So y prime over here, y double prime over here, okay? And there's no the procedure is nothing different from what I just showed you in the last example. Okay. So now I have this y prime, y double prime series, and then just put everything back to the ODE, and then I got this. Okay. So again, the strategy is that, right, so here you have the first series comes with x to the n minus 2. Okay, the second series comes with x to the n plus minus 1. Actually, after you multiply this x to here is also x to the n. And then the last one is also x to the n. So what you want to do, as I mentioned, illustrate in the last example, is that you want all three series comes with x to the n, right? So the second and the third already okay, but then the first one you need to do the shift index, right? So to make this one to looks like x to the n instead of x to the n minus 2. Right? So again, as I told you how to do it already, right? So is that whenever, so this term I write it over here, is that whenever you see n in your expression, right? So you just put it as n minus n plus 2. Okay. So a of n, I see an n here, so then this becomes n plus 2. I see an n here, it becomes n plus 2. I see an n minus here, it becomes n plus 2 minus 1, which is n plus 1. Right. So then this x to the n minus 2, and this n becomes n plus 2. Right. So n plus 2 minus 2. So then it's also x to the n. So then finally, right, so this n plus 2 equals 2. So that means it's n equals 0. So then by that, right, so again, you successfully make this x to the n minus 2 becomes x to the n. Okay. So that's why, again, you can make these three sums, group all these three sums all together. Okay. So, and now, right, so what you do over here, right, so I will just take all this x of n as a common factor over here, right? And then you require all the coefficients upfront is 0. So this is the recurrence relation that you get. Okay. Again, you can see a relation between n plus 2 and an, right? So this, I write it again here. So same idea as the last example, right? So I just separate two cases, odd and even. Okay, so for even, I can express all the terms in terms of A0, right? So for odd, I can express all the terms in terms of A1. Okay. Then from there, I find the general expression for this odd coefficient, and then the general expression for this, I'm sorry, the even coefficient, and then for the general expression for this odd coefficient. Okay. And then this general solution, again, right, so it's a linear combination of two functions. Okay. Okay, so up to this point, I think it's good to take a let's take a 10 minutes break here. Okay, just to make sure that you go through the procedure once by yourself. Okay, to understand how it works. Okay. So, and then actually, if you want, you can also take some time to try to do example 3 by yourself. Okay, so this time the equation is also very simple, but instead of doing this x to the n, I am doing this x minus 2 to the n. Okay. So we'll come back at 12:20. So let's look at this example together. Again, this equation is what you can solve already immediately, right? So you know that this is just the exponential function. Okay. So this time, as I said, right, instead of x to the n, I have this x minus 2 to the n, right? So and you will see why in this case this one is more convenient. Okay, it's actually related to the initial conditions that I gave. Okay, so in this problem, I not just that I want you to find a general solution, but I want you to find a solution right, based on these two initial conditions as well. Okay. Okay. We just use the same procedure, right? So although we have this x minus 2 instead of x, right? So taking the derivative of x to the n is almost the same as taking the derivative of x minus 2 to the n, right? So then I have this y prime, which is just equal to, again, right, term by term differentiation, full factor of n down here, and then x minus 2 to the n minus 1. And then again, take it one more time, and then y double prime is given by right. So this time, extra factor of n minus 1 is up here, and then I have this x minus 2 to the n minus 2. Okay. So again, right. So what you're going to do is to substitute, right? So your series back to the equation, right? So and you know that you're going to do the shift of index, right? So I want to, again, so this term comes with this power of n minus 2, and this term comes with the power of n, right? So I want to have this power also becomes n, right? So again, shifting index, right? So whenever I see n here, right? So I just replace it by n plus 2, right? Such that this n minus 2 become n. So then with that, this is what you will find. N becomes n plus 2, this n becomes n plus 2, this n minus 1 becomes n plus 1, this x minus 2 to the power n minus 2 becomes x to the n minus 2 to the n. Okay. So then with that, right, so substituting this and this back to the equation, the recurrence relation that you find is the following, right? So right. And then again, this common factor of this x minus 2 to the n has to be equal to 0 for all x, right? So that is, right, so this thing itself is equal to 0. And then from that, right, so again, you find this recurrence relation, right? So this a n plus 2 is equals to a n divided by n plus 1 times n plus 2. Okay. So, and that means, right, so recurrence relation, right? So this one, you can see that this is a n minus 2 divided by n plus 1, n plus 2 that I had already, and then also times n and n minus 1. And then you can keep doing it, and then eventually, right, so you see that this an plus 2 is actually 1 divided by or let me just do an instead of an plus 2. So you find that this an over here is given by 1 divided by n factorial a naught. Right, so or depends on odd or even. Okay, it's 1 divided by n factorial a1. Okay, so this is for the even. This is for the odd. Okay. So and with that, right, so you can go back to. Let me open a new page. So that is right. So I have 2 different cases that for n equals 2k. Okay, so this is the case where I have the even coefficient, right? So then this a of n is just given by 1 divided by 2k factorial a naught. Right? And then on the other hand, for the odd, right? So for n equals 2k plus 1. Okay. So then I have this an equals 1 divided by 2k plus 1 factorial a1. So and as a result, right? So you know that you have again two series. Okay, so it's the general solution is the linear combination of your 2 series. So then I have this y of x equals a naught. This series over here. This is for all the odd even terms, right? So and then plus a1 times the other series. Sorry, like this. No. This 1 divided by 2k factorial is already the term. Okay, right? My mistake here. So this is the general solution. So no problem. But now if I want to find out the solution, right? So given these 2 initial conditions, right? So what do we need to do, right? So is that you see that now it is easier to do this x minus 2 series, okay, instead of this series in terms of x, right? So because if you put this initial condition, right? So what is the initial condition that I give, right? So I have this y at x equals 2 equals 1. So I just put 2 into your series, then because you can take advantage of the fact that I have this x minus 2 over here, right? So if you just put x equals 2 in all the terms, right? So you will see that most of the terms will go to 0, right? So except the a0 term, right? So if I put x equals 2 in the series, you'll find that y2 is equals to a0. So however, right, so if you when you first do the problem, if you just treat it as x to the power something instead of x minus 2 to the power something, then now if you put x equals to 2 into your series, you will see that all the terms are non-zero. So that means that you have to your initial condition, right, so will depends on a combination of all the of many this all the terms in this series. Okay, so which you actually need to do the sum of them. Okay. So and similarly, okay, so if you go ahead and make use of the other initial condition that I gave you, so y prime of y prime 2, okay, so the derivative at this value here, then you will find that a1 is given by -1. So that is, I'm just going to replace it, right? So this is y2 is a0, and that's why a0 is 1, and this is -1. So this is the result. Okay. So and you may go back to ask, what about if I go back to just use the regular method that you learned before, right? So you know that this y is actually some constant times e to the x plus the other constant times e to the right. So it's this e to the x plus this e to the minus x. So and is it the case over here? So in fact, this one itself is not e to the x, and this one itself is not e to the minus x. Okay. However, I'll tell you what this one is. So this one is actually this, right? You can actually verify it by yourself, but this series actually represents this function here. Okay. And this function actually has a name. Okay, if you know this hyperbolic, it's called a hyperbolic cosine. Okay. And the other one, this one is by itself is not just e to the minus x, but it's actually this one. Okay. And this is actually called a hyperbolic sine. Okay. But you can see the equivalence, right? So you can either treat the solution as a linear combination of this function and this function, right? So that will be completely the same as the linear combination of e to the x and e to the minus x. Okay. So then this is just a summary of the procedures, right? So I don't need to talk about it one more time. Okay. So and the next is that we are going to deal with the case where this p and the q functions are not so well behaved at some point. Okay. So in the what I mean is that I have some so-called singular point for this p or this q function. Okay. So the definition of singular point, right? So is that if I have this p function, q function to be analytic at that point, right? So then that is known as an ordinary point. Okay. So otherwise, that would be a singular point. Okay. So in the example that I'll give you, you show that you see that what I mean. Okay, but essentially you just basically deal with this 1 over something. Okay, 1 over x or 1 over x minus 1. Then you can see that this is the so-called singular, right? So this is singular at x equals 0. This is singular at x equals 1. So in the previous example, we don't have any functions that looks like this. Okay. So, and this is an example. Okay. So I have this equation here, right? So I am going to write it in this form, right? So if I want to write in this form, I don't want any coefficient function for the highest order derivative. So that what I do is that I divided the whole thing by x squared. Then this is the equation that I have to deal with. Right? So then you can see that, right? So this will have a singular point at x equals 0. So where this 1 over x squared tends to infinity, right? So that at that point you cannot express this 1 over x squared as a convergent power series. Okay. So what if we just again try to use the same strategy? Okay, so without worrying about this behavior, and what you get? Okay, so if you go ahead and do that same series, and then you will find the following result. Okay, so up to this step, okay, so what you see is that you cannot find a recurrence relation. Okay, so you just have this whole term to be 0 by itself, right? But you can see that this is not a relation between an and an plus 2, right? So this whole term here just have this an by itself. And the reason is because, right, so because in this whole process, this time, you didn't do any shift of index, right? So because this x to the n minus 2, okay, is multiplied by this x to the power 2, right? So that's why in the first sum, you have x to the n, and the second sum, you also have the x to the n. So then there's no need for you to do any shift of index. And because of that, you cannot find a relation between this an and an plus 2. So now I have this coefficient to be 0, and that tells you nothing but an itself to be 0. Okay, so because, right, so whatever n you put in, right, so this n times n minus 1 plus 1 would be non-zero. So that an has to be 0 for any n. And if that's the case, right, so then you just put in this an equals 0 over here. That means the solution is just simply 0. Right? So then this is well, this is just a trivial solution to this equation. Okay. So that is we now run into problem, right? So we are not really able to find a solution, find the solution that we want for this equation. Okay. So here is another example. I have this equation, and then again I divided both sides by this x squared minus 1. Then again you can see that I have a function that has a singular point. Right? So this time the singular points happens when we have this x squared minus 1 equals 0. So that means x equals plus or minus 1. Okay. So this time, if I again try to use the series solution, okay, this time it kind of works again. Right? So you go ahead and take the derivatives and then put everything back. No any other new tricks really, and you'll find that you have a okay recurrence relation that you can use, right? So this an plus 2 related to this an by this factor here. Okay. So however, okay, so if that means you do have an infinite series that you can write down. Okay, but even though you get this infinite series, and then if you go ahead and test the convergence of the series that you get, you realize that that series will converge only in this range. Okay. So that is the series that you get will not converge at these two singular points. So Then in general, so what happens is that if you have this ODE, okay, so with this singular point, okay, you can still use the series method, okay. So, however, the series that you get will not converge at the singular point. But now you have these two different examples. So one not working, the other working. So why is that? So it's because when I let the series, okay, so when you let the series, okay, so the point that you pick, this x0, cannot be at the singular point. So because in the first example here, the singular point is at x equals 0. But the series that you are trying to use is this one. It's an times x minus 0. So that is, you are trying to have this series about that singular point. And that's why the whole thing won't work. In this case, right, so on the other hand, right, so the x0 that you pick in this series, again, is 0. But because your singular points are not at 0, that's why you can still go ahead and find your series. Okay. So therefore, right, so the general strategy is that you look at your equations, right? So if you find out that you have some singular points, then you can still try to use this method, right? But this x0 that you pick has to avoid the position of your singular point. So now there's just some more details. Okay, so for these topics of singular points, I won't go very deep into it, but at least I just want you to see that sometimes this singular point can appear and it will just stop you from solving it. Okay. So in fact, there are two types of singular point. Okay. So suppose I have a single point. Okay. So if you take the limit, okay, so for this, okay, what you're doing here is that you have this p of x, right? So times this factor here. And then you have also tried another limit, which is the q of x times the x minus x0 squared. So you know that when you have singular points, so that means this p of x is 1 divided by something like x minus x0, or even 1 divided by x minus x0 squared, or something like that, right? So, but if you multiply this factor, okay, it might actually help you to remove that, right? So to give you some finite value. But anyway, so if you do these two limits and find that they actually exist, that means you can obtain some finite numbers. So then this x equals x0 is called a regular singularity. So otherwise, it is known as an essential singularity. So for example, okay, so if in this equation, you do have a singular point, so you can see that this x plus 1 equals 0 when x is minus 1. So in this case, is this a essential singularity, or is it a regular singularity? So what you need to do is just that this is your q of x, right? So in this case, so you are going to do this limit, x tends to 1, so x minus 1 square times this q of x, which is 1 divided by x plus 1. X tends to minus 1. X plus 1 cube. So then what you have is the limit of x tends to minus 1, and this is just 1 divided by x plus 1. So then this whole thing still blows up, right? So you cannot have a limit, and that's why this is the known as the essential singularity. So for regular singularity, okay, so on the other hand, okay, so that you can still find a solution, okay, so in terms of this the known as the generalized power series. Okay, so what is a generalized power series? The generalized power series, if you look at it, is that you have this regular power series over here in the sum, but this has to be multiplied by an extra factor of x to the c. Okay, and this c is something that is to be determined, and it can be non-integer. So for more details, okay, you can look for this method here. Okay. So I don't have any exercise problem for this part. As I said, I just want you to be aware of the fact that, okay, sometimes you do have these singularities and may not be able to solve it using the method that we just saw. Okay. So the next part, okay, so it's just based on the two kind of differential equations that you see again in physics problem. Okay, so and in this case, we have something interesting going on, is that you try to let the solutions to be an infinite power series. Okay, so but under some special conditions, you find that not all the coefficients in your series terms are non-zero. Okay. So I'll explain in a minute. Right? So that means you have A0 to be non-zero, A1 to be non-zero, up to maybe AN to be non-zero, and then suddenly AN plus 1 is 0, and then AN plus 2 is 0, and then all the subsequent terms are just 0. So then in that case, you are just going to have a finite polynomial as your solution. Okay, so instead of an infinite series. Okay. So there are two, as I said, there are two differential equations that I want to talk about. Okay, so and you'll see that again in physics problem. Okay. So the first is known as the Legendre differential equation, and the solution that I'm going to talk about is known as the Legendre polynomial. Okay. So I won't talk about from which physics problem you'll see this, but I'll just say that when you solve for this partial differential equation in spherical coordinates, then you will have to deal with this differential equation. Okay. So when you solve partial differential equation means that your equation involves function of 2 or 3 variables, right? And then you the equation involves partial derivatives, right? And the method that you are going to learn later is that you are going to basically decompose this one partial differential equation into 2 or 3 ordinary differential equations. Okay. And then when you do that, in some cases, you will arrive at this so-called Legendre differential equation, which is still an ordinary differential equation. Right? So first of all, if we look at it, we see that it does have singularity. Right? So if you divide both sides by this 1 over x squared, right? So then you have this 1 minus x squared in the denominator, right? So that's why you know that again you have singularity. Okay, so at x equals plus or minus 1. So and in that case, so it will still be a regular singularities, and you can still use this power series, but you know that your power series won't converge at the singular point. Okay. However, in the physics problem, okay, so as you will see when you actually use it, is that you want your solution, okay, so to be converged also at this x equals plus or minus 1. Okay, so that you need that. Okay, so and in that case, you realize that if the L, which is the parameter, okay, just a parameter that you imagine that you can change, okay, if your L takes some special value, okay, so you find that this infinite series solution will be truncated to a finite polynomial solution. So then in that case, okay, so you don't worry about the divergence or convergence, because if you have a finite polynomial, okay, so then it must be convergent. Okay. So let's see what's actually going on. Okay, so we again just use the same old trick. Okay, so not going to explain it one more time, but here you find the recurrence relation over here. Okay, so and then you are going to just again separate out with the odd and even case, right? So even case here, odd case here. Okay. So now look at this term over here. So I have this L minus n in my numerator. So it is possible to be 0. Okay, so if I have this L equals n. So and of course, right? So what is this L? Right. So as I said, right. So this would be a parameter that in your differential equation. Okay. So or in other words, right. So if you hope to see that this L minus n to be 0, then you are forced to select some L that can satisfy this. So this n, of course, is an integer, right? So that runs from 0 to infinity, right? 0, 1, 2, 3, and so on. Right? So then that means if you pick L to be also some finite integer, right? So then at some n, right? So you see that this L minus n will be 0. And then that is this recurrence relations won't continue anymore. And you can see the real example over here, right? So if I just go to write out all the terms, it's over here. Right? So if your L is 2, then you see that this L minus 2 will be 0. So this term will go to 0. Okay. And then the next term and all the subsequent terms will actually also go to 0, right? So because of this relation. So, and on the other hand, right? So if I give you another example, is that if L equals 3, right? So then you can see that this whole term becomes 0, and all the subsequent terms will also become 0. And then again, you get a finite polynomial. So that is to say, right? So given these general solutions, right? So if you pick a positive integer L, right? So you'll be able to truncate one of the series. Okay. So I said already, right? So if you put L equals 3, then you are going to truncate this series. Okay. But if you put L equals 3, you are not be able to truncate the other series. Okay. So similarly, if you put L equals 2, you are going to truncate this series, but this one will still be an infinite series. Okay. So that is, pick any L, you will be able to truncate one of the series. And here, just a summary with what I said. Okay. So, and the series that get truncated or get terminated, okay, will give you a finite polynomial, okay, of the order L. Okay. And that is called a Legendre polynomial. okay, and we denote by this P subscript L. And the other series that will still diverge will be called Legendre function of the second kind. Okay, so and it's the Q of X. Okay. And that, therefore, right, so for any given integer L, so the general solution can be written like this. So here, I just show you how the first few orders of the Legendre polynomial looks like. But again, okay, so once you actually need to solve this polynomial in your physics problem, okay, you might go back to review this. Okay. So the second equations that give you this finite polynomial solution is called the Hermite equation. Okay, and the finite polynomial solution is called the Hermite polynomial. Okay. So I should be able to have enough time to talk a little bit about the origin, okay, of this equation. Okay, so but first of all, just look at this equation by itself. Okay. So here, this time actually is easier to deal with in the sense that we don't have any singular point in this equation. Okay. So again, lambda is a parameter. Okay, so that we can choose. Okay. So with that, right? So you can just easily find the recurrence relation, and then you find that the solution is a linear combination of these two infinite series. Okay. But here again, you see one thing is that the numerator, right, so can be 0 at some n. So given that you choose some value of lambda, right? So here you can see, right? So if I choose lambda equals 4, right, you can see that this term will become 0, and also all the subsequent terms will be 0. If you put lambda equals 6, right, so then this term 0, and all the subsequent terms will be 0. So that is, if you put lambda to be equals to even integer, okay, so then you are able to truncate one of the series. Okay. So, and for even integer, okay, so I can always write this lambda as 2k, right? And still I have two different cases, right? So one is that the k itself is an even integer, and the other case is that the k itself is an odd integer. Okay, but in both cases, of course, lambda is even. Okay, it's just that if you have k to be even, then what do you have? You have either 2, 4. I'm sorry, 2, and then if it's even, it's like a 4, and then a 4 times 4 by 16, and so on. Right. So, and then if this k is an odd integer, so what do you have? Like 2, and then 6, and then 10, and so on. Right. So, but in any case, right? So you can truncate one of the series, and then these are the first few terms that first few Hermite polynomials that you can have. Okay. So again, so for this case, let me just tell a little bit about where this polynomial, where this Hermite equation comes from. Okay. So in quantum physics that you learn, you'll be solving the Schrodinger equation, right? So basically, in particular, so I'm talking about the time independent Schrodinger equation. Right? So then in one-dimensional problem, then the equations that you have looks like this. Okay. So the psi is the wave function, okay, and then the v of x is the potential that your particles is in, and then E is the energy of the wave function. So in particular, okay, so if you are in a harmonic oscillator potential, okay, so then this V of x is given by 1/2 m omega square x squared. So then the key is that we want to solve this equation. And if you go to let this psi of x, actually before we do that, actually I need to do a scaling of the variable. Okay, so if you let another new variable, okay, x1, which is equal to a scalar times x. Okay, so then if you actually do that, you just simplify the prefactor a little bit. Okay, so and after that, you let the solution that take this form. Okay. If you let your solutions that take this form, and then put this back to this original Schrodinger equation. Okay, so h of x1 is something that you don't know what it is, and you want to find out what it is. Okay, so this exponential or this Gaussian terms, right? So basically have this decay behavior, right? So as you go to x to be a large number, right? So then that's what you want, because you want the wave function to be kind of localized in some finite region of x. Okay. So, but anyway, if you actually put this form back to the Schrodinger equation, okay, so you find that the h function has to satisfy this equation. Okay. So, and if you compare this form, okay, so to what we just had here, you see that this is a Hermite equation. Okay. And this is what I call lambda. Okay. So now, if you see this, right, so you can solve it using the series solution. Okay. So then why in this case, we are also interested in the finite polynomial, right? So if I give you the infinite series, it's also a solution, it's also satisfy the Schrodinger equation. However, it turns out that if you indeed, right, just look for the infinite series, you'll find that, right, so that is, you're going to let h to be again like a series like this. You will find that if you indeed look for just an infinite series, but don't care about the truncation, you'll find that for large n, this a of n goes like 1 divided by n divided by 2 factorial. Okay. And because of that, you see that this h will goes like e to the x1 squared. I'm not going to give you all the details here, but you can just take my word for it, is that if you allow the infinite series, okay, you'll find that the behaviors of this x function goes like this, okay, for large x. And then if it in this the case, then you run into problem, because if h is indeed go like this positive exponents here, and then if you multiply it by this e to the minus negative x1 squared divided by 2, then you still end up with a positive power up here, right? So, and what it basically tells you is that the wave function getting larger and larger and large x. Okay, and that's unphysical. Okay, so we are looking for the wave function that are localized okay, so which is kind of bounded by the harmonic oscillator potential. Right? So therefore, we want to look for the solution which is not infinite series. Okay, instead is the truncated polynomial. Right? So then in that case, right? So I have requirement for the lambda, right? So the lambda has to be equals to 2k, right? So for k is any integer. So that is to say, you have requirement on this parameter. So that is 2e divided by h bar omega minus 1 has to be equal to 2k. Right? So k can be any integer. And that actually gives you the requirement for the energy. You see that this energy of the system will have to be satisfy this relation. Okay, if you want to have this localized wave function, and this k, not any value, is a 0, 1, 2, 3, 4, 5, 6, and this is the energy level for your quantum harmonic oscillator. Okay. The ground state is like 1/2 h bar omega. Okay. Every state that you go up, right, so you increase by h bar omega instead of having a continuous increase in your energy. Okay. So I'm sure that you learn this one more time in the future. Okay, so I think this is all I have, and I guess I'll just end the class for today. Okay, if you have any questions, you can ask. Okay. So otherwise, okay, so see you later.